Welcome to Math with EJD. In this video, we're talking about nonlinear PDEs and shock waves. I'm very sure you've heard about shock waves before, especially maybe in when earthquakes happen and things like that. So shock waves are bound to happen. So we can also see that can be stretched into fluid dynamics and sudden traffic jams and all that. So we have some kind of shock waves. Let's see what PDEs have got to do with shock waves. So I think this, okay, yeah, I mean, we've seen some nonlinear partial differential equations before now. So nonlinear PDEs arise when the unknown function and the unknown function, usually u, it doesn't have to be u, it can be anything. When the unknown function or its derivatives appear non-linearly. What that means is that if the function u, for instance, is squared or you have its derivative more than power, having degree more than one, or you have a product of the not unknown and its and any of its derivatives. So those are non-linear situations, right? So they appear non-linearly. Okay. So these PDEs often model physical phenomena with discontinuities. So they're meaning there are jumps. So, and those discontinuities look like shock waves in fluid dynamics, or even sudden traffic jams, or sudden traffic jams. Okay. So one classical example is the Berger's equation. And that is partial u partial t plus u partial x equals nu, or call that v, partial squared u partial x squared. And here, u of x comma t is the velocity. It is the velocity if you're talking about a fluid flow. If you're talking about traffic, that would be something like traffic density. Traffic density. Then you have nu greater than or equal to 0, and that will be the viscosity for fluid flow, or diffusion. That's the viscosity or diffusion coefficient. Okay. Then when nu is equal to 0, it becomes the inviscid Vegas equation. So that's, in that case, it becomes homogeneous, right? It becomes the inviscid Vegas equation. I want that to be as clear as possible. The inviscid Vegas equation. Which is partial u partial t plus u partial x equals 0. Okay. So what makes this nonlinear is actually this term. You have your known function and you have its derivative multiplied together. That makes it nonlinear. Okay. So this nonlinear hyperbolic PDE, nonlinear hyperbolic PDE. Why is it hyperbolic? We have ABC. So, and they're all 0. So should it even be hyperbolic, or Oh, okay. The original expression. Yes, the original expression is not is hyperbolic. Yeah, get it. Okay. This nonlinear hyperbolic PDE exhibits shock formation, what we call shock formation, because it is smooth. So it has smooth initial conditions. It means smooth initial conditions rather can now develop discontinuities, discontinuities in finite time, in finite time. Okay, so we switch over and have this now, and then I want to take it along with green. Okay, so let me go for this at this point. So let's look at some applications. Applications. So imagine, like we've been talking a lot about traffic flow, traffic flow. So here, the u of xt, the unknown we are looking for, will represents car density. So how many cars you have in the traffic. So car density or even speed. So traffic jams form as shocks. That goes. Then we have fluid dynamics. Fluid dynamics. So simplified one-dimensional models for compressible fluids. Okay, in that situation. Then we can also have it in gas dynamics. Gas dynamics. So modeling of pressure waves and explosions. Okay, so let's go on as we take one example. Yeah, we take one example and that will suffice. So example. So the example will be about shock formation in inviscid Berger's equation. So that means we are looking at the homogeneous Berger's equation. So the question is to solve partial u partial t plus u partial x equals 0. I think we've seen this type before when we're talking about method of characteristics. So okay, it's not done with initial condition. Initial condition. So the initial condition here is like in step format. So you have u of x comma 0 equals, that is in the beginning, when time is 0, you have the fluid flow, or the traffic is actually the speed of the traffic or density of traffic is 2 when x is less than 0, and then it's 1 when x is greater than 0. Okay, that's the space. Okay, so we go for the solution. Okay, like I said before, we used method of the characteristics. So use the method of characteristics, where we know that um, along characteristic curves, along characteristic curves, dx dt equals u, because it goes with, so dx dt equals u. So we see that here, u is constant. Okay, u is constant in that case. So we can just say u is equal to c1 or anything like that. Then we can also say that, yeah, so that goes, right? Then talking about the initial point, initial condition. So initially, right? Initially, for x less than 0, we know that u is equal to 2. Okay, from this place, x less than 0, u is equal to 2. So we can say that dx dt is equal to 2. And if that is the case, that simply means that dx is equal to 2 dt. Integral of dx equals 2 integral of dt. So that means that we have x equals 2t plus a constant, which we can call plus a constant, right? But we know x is less than 0. So we just have the initial value of x not there. Okay. Then we go for the next one. For x greater than 0, we have u to be 1. So dx dt is equal to 1. And that implies that dx is equal to dt, meaning the integral of dx is equal to integral of dt. Integral of dx is x, integral of dt is t, plus x naught again, the initial space. Okay, so now we can then go ahead and say thus, we have two families of straight lines, two families of straight lines with speeds 2 and 1 respectively. Okay. So then we move on to say that at x equals 0, there is discontinuity. There is discontinuity. Why is that so? The initial condition tells us that already, because the u is 2 when x is less than 0. U is 1 when x is greater than 0. So we don't have anything for when x is equal to 0. Okay, we don't have anything for that. So there's no speed, maybe more like 0. So we say that at x equals 0, there's discontinuity. So characteristics from left, the characteristic from left is faster because the speed is 2, right? Because when x is less than 0. So that now overtake characteristics from left, which is faster, overtake those. Overtake those. They overtake the characteristics from right. So in that case, that leads to shock formation. So we have a shock formation like that. So the shock speed S, the shock speed S is found by the Rankine Hugoniot condition. And what does the condition tell us? It says that Fs, small s, okay, I guess this is where I get to change ink. So S is f of ul minus f of ur. That should be left and right. So ul minus ur, where f of u is equal to half u squared. That's a Rankine-Hugoniot condition. So now here ul is 2. That's the speed from the left, and ur is 1. Speed from the left simply means when x is less than 0, and from the right when x is greater than 0, just like that step function initial condition already gave us. So with this in place now, okay, with this in place, we just know that f of 2 would be half 2 squared, which is half into 4, and that is simply 2. Whereas f of 1 is half into 1 squared, which is half into 1, and that is simply 1 over 2. Thus, S would be 2 minus 0 0.5, referring to this now, f of ul. So that's 2 minus 0 0.5 all over 2 minus 1, okay? And that is 2 minus 0 0.5 is 1. is, yeah, 1.5 all over 1. And that is simply 1.5 overall. So we can go for the final solution then. So we have the solution to be, the final solution is u of x comma t equals 2 for x less than, what did we have there before? We had x, right? X less than 0. So u of xt will now be x less than 1.5 time, okay? And 1 x greater than 1.5 of time. So in that case, we can say that the shock, the shock, which can either be traffic jam, or discontinuity, fluid discontinuity moves rightward. It moves rightward with speed, 1.5. That's because this one is moving so fast, it overtakes this. So this is coming from left, while this is coming from right with speed 2, and this is with speed 1. But the cumulative speed will just be in the rightward direction, okay? And that will be 1.5. That will be 1.5 based on our calculations, okay? So that's what we have right there. So I take that again. So this is saying that we have moving rightward, we have something with speed 2, and that's from left to right now. So left to right motion. And then we have this one, coming from the uh right. Okay, should I just say right to left motion? And that is coming with 1. Well, the overall effect is rightward, and the speed is 1.5 based on our calculations. So we have, of course, we always have a Python code to show us what is happening. So if you look at this now, so we have the simple code right here. Um, you know, we define the initial condition, x is less than 0, and that is 2. Otherwise, for x greater than 0, we have 1.0. So method of characteristic solution before shock tells us that x naught is x minus initial condition times t. Then we return the initial condition. Then we have the division into this number of spaces, and then we talk about the times. And with that, we just have something this beautiful. So at time t, we have this blue line. At time, okay, you see this is coming from here. We have this now coming with speed 2, and this is coming with speed 1. Okay, so at the end of the day, so at time t equals 0, we have this blue. Then and then we have 0 0.2, 0.4, 0.6, and 0.8. And from what we saw already, we have a cumulative movement with you know speed 1.5, like that. So this is what we have in that situation. Do we have practice questions? Let me check. Um, so this looks like something pretty that we can work with. Okay. So I guess we can get one or two of this. Okay, practice. Practice. Okay. Um, okay, we've done this 3, 1, 5, 2, 10. Okay. 1. Given the initial condition, for the inviscid Berger's equation. Okay, we have u of x comma 0 equals 5 if x is less than 0 and 2 if x is greater than 0. And A, we need to find the speed. Find the speed of the shock wave using the Rankine-Hugenoit condition. B, determine the location of the shock after time t equals 1. The location of the shock after time t equals 1. Then number 2, okay, for number 2 now, solve the inviscid Berger's equation. Partial u partial t plus u partial x equals 0. Oh, okay. Did I write this one? It's the same Berger's equation, right? Now with 5 to. Okay, yeah. I mean, yeah, it's the same equation like the one I'm writing now. So it's the same equation all the way. So I didn't write it, but it's been stated that the inviscid Berger's equation. So exactly this, right? To solve the inviscid Berger's equation for the initial condition, u of x comma 0 equals sine x. Okay, so A, find the solution. Find the solution using the method of characteristics. Of course, you can also run the Python code. I suspect this is going to give some oscillatory kind of behavior, or yeah, because of the initial sign condition. Okay, then D now, describe the behavior, describe the behavior of the solution over time and determine if shock formation occurs. Okay, so let me see your answer in the comment section, either on Facebook or on YouTube. And also feel free to let me know how helpful these videos are for you. And be sure to tell me if there's a problem you'd like me to solve or a topic you'd like me to teach. If you have not subscribed, be sure to do that also. And after doing that, hit the notification bell so you can always get alerted each time a new video is released. And lastly, like and share so that more people can have access to the great content we have going on here. Now we have more than 700 videos, a whole lot. It's a school, a mathematics school of sort. Okay, so please avail yourself the opportunity and get your maths going well. Till I come your way again, keep doing maths right. Bye.